that is essentially recovering a notion of substitutivity for both assumptions, right? For the assumptions that are true and for the assumptions that are boxed in Convert's sense, okay? Which in our terminology here means that they are valid. So this is the substitution property we will use. So we're going to say why. So sometimes this is called the modal substitution property. So we'll use this by the substitution, by this modal substitution lemma. Using D. Okay. I should say E and D according to my lemma. Right, makes sense? Okay, great. So now we can actually prove this this theorem, which is essentially a notion of reflexivity. Okay, it basically says it's true for everywhere, A is true everywhere, so it's true also for me. Okay? So this is typically a law we want, and if you would look at the model theory of modal logic, this corresponds essentially to the reflexive accessibility relation in the model theory view. And how do we prove this? Okay. So how would you prove this? How do we prove A from this assumption? Yes.
We use the elimination principle.
We use the elimination principle, okay, to preserve validity forever. Okay, so we're going to prove box A. Put in true here. And prove box A. Okay. Now we can move it into our main valid context, okay, as something A is valid. Okay, and we still have the fact that X box A is true. And we need to prove A is true. Okay, but then this is done essentially by our second, our purple. Let's make this purple. Our second move of how we deal with essentially valid assumption. So we're going to use here the validity, and here we're going to use the fact that box A is true. So great. That was good news. Okay, that we can actually prove one of the laws of modal logic. And this law is often, sometimes it's also called, for whatever reason, I don't know what the background is, maybe malaria. It's called T. Okay, I don't know why it's called T. But this is the law. Okay, so let's do maybe one more proof. There are two more laws that S4 in fact satisfies. So there's reflexivity. And we also have distributivity. And which essentially says that I have A implies B necessarily true, and I have A is necessarily true. I now box B. So B must be necessarily true. So it distributes over implications. I'll leave this proof to you as an exercise. I'll do a simpler proof, which is also true, okay? Which is the essential law of S4, sometimes called 4, which essentially encapsulates distributivity, transitivity. Often it's just referred to as 4. And that says that if I have box A, that implies box A. And I want to do this proof because it highlights that we have to use these rules in a specific order. So we start in the empty context, okay? And we want to prove box A is true. So we use our implication rule. Okay, easy. And we add in box A is true. And that means we now need to prove box A is true. Yes.
Box introduction.
So if we would use box introduction, thank you for bringing this up, we need to clear out our local context. Okay. So that's not the best strategy because then you're left to prove box A without anything. And that will be difficult. So we know this is true necessarily, okay, so we want to preserve this truth, okay, forever. And how do we preserve things forever?
Elimination.
We use the elimination principle, exactly. So I'm going to start this with purple just to emphasize this again. So we use the elimination principle to prove from these assumptions A true proves box A true. Okay. And now we can preserve it. Okay. So we have here our new assumption, U, which says A is valid. And we still have the old one for now. Okay, so it doesn't do any harm. And we need to prove box A is true. And so now we can use the introduction box, which will clean out the local context, okay? But our valid context will preserve. So we have one box still left, and we can do the same thing again. Okay, so we'll strip off the next box, and we end up needing to prove that we have from U, which is valid, describes A is valid. We need to prove A is true, and that means yes, okay. We have our assumption as valid, so it's also true. So the important part is that if you have this let style format, right, then you're forced into a particular way of proving things because you want to make sure that the parts that are, necessarily true are really preserved for eternity. And you do that usually with the elimination. That's how we go about this. Yes?
Is there a way to understand why the box introduction rule clears out the local context?
Well, if you think about what it meant, right, for something, so validity, I said, internalizes this idea of box, so actually what I say, box A internalizes the idea that A is valid. Okay? So this is a syntax for saying A is valid. Okay? This is saying what the meaning is of box A, namely that A must be true without any local assumptions. So we must clear it out. So if we have, so if we want to actually prove something that is box A, like here, it's always a good strategy. Okay? And in fact, you can prove that it is, you don't lose anything by doing this, by prioritizing essentially the elimination principle here, or box, to move essentially this assumption, which is box A, over to the valid context. So I'll give you proof terms for this, and that will be clear why I call it a let elimination rule. But the idea is really here, like this rule here, you don't lose anything. You actually gain information as you go up and continue to prove C. So that's always a good thing, if you gain more. This rule here, we actually lose something. We have to give up something, right? Because we are committed to proving that A is valid, meaning that we cannot rely on our assumptions. Because this is going to be true for everyone here in this room and beyond. Okay? And so they don't know what I know. They don't know what you guys know. Okay? So all they know is like, I don't know, whatever is in here. Okay? Possibly empty. Okay. So far so good? Okay, yeah. So what are these proof terms? And it goes back to your question about like, why did I say it was let elimination rule? So when we want to have proof terms, we're going to change this idea of H rule, right, to something we have here a term. Right, that says the term M has type A. Okay, so M has type A. Or you can read this as saying M is a proof witness for this proof A. And what kind of proof terms will we have? Well, we'll have all the proof terms we have before. Oh, look at that. There's a new board. I didn't realize that. I was like, new boards I'll make use of that. Well, we have terms. Okay, and we have variables. Max, applications, and we have pairs, okay? And we have then first and second, so we have all this stuff. We have case for disjunctions, but in particular now we have proof terms for box. And we have two different kinds of variables, right? So this is our x, this is our ordinary variable that we have already. That's the variable that was bound by lambda. So for example, here in the introduction rule, we added to gamma. Okay. But there's another kind of purple variable, okay, that binds things that are valid. So there are really two kinds of variables. And this is visible here in these two rules. So we don't want to confuse them. So we have u, which is going to be for valid assumptions. Okay. We're going to introduce, we're not very creative, we're going to just call this box, okay? Literally box. And we're going to give this a name box. So if I come here, right, and I say, the variable here is going to be y. Okay, just because I called this guy here y. Let me name this u. Names are generally not that important, but helpful. So let's call it u. And that means we're going to keep okay? And in here, what will this term that's necessarily closed with respect to my local assumptions. Okay. Definitely closed. So, and what I have in the bottom, essentially, it says that I have box M. Now, box M essentially says, you can think of this as saying, essentially, I package a piece of code or a term or an object that is closed and I mark it as such. But it is necessarily closed. And because it is closed, the idea is that I can give it to everybody, okay? And you can run it, okay? Because it's a closed piece of code, as long as you have a compiler for whatever language that is, okay, you can run it. Okay? It doesn't need to be spliced into some particular runtime environment. It doesn't rely on any libraries, okay? It's just a valid piece of code, literally valid, okay? And it should be able to run everywhere. Yes?
Is there a reason why in the term language we only have functions that abstract over X type variables and not new variables?
Not new variables, yeah, there is a reason, because that's what we're doing here. Okay. Need more space. And we rewrite the rule. I will rewrite the rule. Okay. I know, you're right. Okay, so what this turns into, give us a bit more space for our proof term. So this is going to be some term n that proves box A. And over here, okay, we are going to introduce this assumption mu A, valid, and it's going to prove C, okay, and the proof term for this is going to be some n. Okay, so in the conclusion, we have a proof of C. But we need to keep track of all the pieces, right, of M and N, which possibly depends on this view. Right, so this N might refer to this view. And so the proof that we're going to have is going to be a let formulation that basically says M will be evaluating to something of the form box. Okay? And so M will be at some point some kind of box M thing. And intuitively we want to bind this M to this whatever sits inside the box. And N is the body. And that's where we're going to use this view. So this is the finder. Yes.
As you said that it has to be closed, does it mean that it cannot contain variables from delta?
It can contain variables from delta, you're right. Okay, so, but it cannot, because, for example, I could prove A because here I have an assumption valid. But it's closed with respect to local assumptions. Yeah? Very good question. And this is important. And we can always depend essentially on global assumptions, on things that are true everywhere. But box will basically say, ah, this is the T. I was looking for the T. Oh man, Zina, I found the T. Sorry. Yes. Okay, so we can actually give some programs for these proofs we did. So what's the program for T? What's the program for this guy? Anybody?
We start with the lambda.
We start with lambda. Excellent. We'll start with lambda. Calling it x. Okay. Going to be a box A. And then, what is it doing then? Okay, so I didn't put the name of the rule here, but the name of the rule was box elimination. Yeah, and it introduced y here as a variable. So the proof term for box elimination is going to be a let. Okay, so we call it y. It's going to be bound to what? X, very good. In, and what are we going to return here?
Y.
Y. So it's a form of run. Okay, so you have a closed piece of code that maybe you have generated, or it's like some kind of syntactic representation that you get passed. Okay, so like passes you this piece of code, 3 plus 2. Okay, not yet evaluated, but this piece of code, syntax, AST, 3 plus 2. You get it. Okay, box. So you know, oh yeah, it's syntax. Again, closed, 3 plus 2. You take it out of the box. Y will be 3 plus 2 then, okay, and then you run 3 plus 2, and you return 1. That's kind of the intuition here. So this does indeed have an analog in our programming world, in the sense of run. Running generated code. Okay, great. So now I was referring to this one. But maybe we can see what our reduction rules are. Okay, so here we had our local sandwich argument, as a true. So we have some proof n. Okay, so that was our box A. And so here we have box M. Okay, and then we have our elimination. Okay. And the elimination will then say, well, it's going to be a let. So let u box M in it. So it's going to be of type C, because here we have something of type C. And then we reduce it. Okay, so we basically said, yeah, okay, we can use the substitution lemma. Those are the box elimination, which is very new. And we said, oh yeah, we can use the substitution lemma. And what the substitution lemma was doing, it was plugging an n for this u. That's what it is doing. So it's a bit of formula of pattern matching, if you like. Okay? how it matches on the structure of this code. It was box, like kind of our pattern. Looks inside, U is the pattern variable, it binds U to M, and then it passes it on. Okay, so what this is happening here is, say, we have M for U and in some formulations, we mark this substitution operation a little different, so sometimes you see this with these double bars, because it is kind of doing substitution for a different kind of variables. U looks for the U variables, and as somebody pointed out, U variables can appear under the box. Okay? So if we want to define substitution, we need to continue to substitute under the box. If we have for the ordinary variables, they cannot appear under the box, we can, for example, stop. So it is useful, I think, to actually distinguish between these two kinds of substitution operations because they do a little different things. Yeah.
Sorry, can you explain the substitution?
Okay, so if you want to do substitution, okay, so the ordinary one, right, saying M for X in some N, so intuitively you find the X and you replace it, but one of the cases will be M for X in box N. Okay. But I know that N is closed according to my rule here. Okay. And therefore, this X, right, the ordinary X, cannot appear in N. So that means that it will not continue to push the substitution inside and it will return box of N. But the other operation, right, which looks for these valid terms, well, these purple variables or the U variables, right, the valid ones, they can appear in here because, according to my typing rule, yes, it's close with respect to my local variables, but it's not close to with respect to my global variables. And in fact, we've seen already here some terms that where this is being used. So here I need to continue to substitute. Okay, so this is the inherent difference between these two operations. And it's useful to sort of actually keep them separate. So in several papers, you see that they're differently defined because they also are for different kinds of variables. Or they do, right? Intuitively, they look for the X or they look for the U, but they will behave somewhat differently. And also, kind of the capture avoiding conditions, they might play into a bit of a different. Yes. Yes.
Yeah. So we have valid variables and we have locally true variables. If I'm pretending I'm coding with this functional language, what's going on? Like,
Okay, we give you a program, right? We're going to write some program. Excellent. So we'll write a program. And the canonical, okay, I want to do a, not the canonical example, I want to do a nicer, more interesting example. Canonical example would be the power function. Okay. I'm going to do my slightly different function, namely the nth function. So I want to write a function n, which takes in an integer, and then it also takes in a vector. So let's say it's a Boolean vector. And then it returns the nth element out of this Boolean vector. So it's going to be some bool. Okay. And so we think of this like this. But we want to write this program in such a way that when we call it partially, okay, with this integer only, we're going to generate a function that is going to be necessarily closed and can be run by anybody. Okay, but this type doesn't capture this for now. Okay? Particularly, you could have, maybe your favorite example to write this would be to say n of I, and then you have your vector, and then you write it into the code. But this means, if I want to run it partially, right, n of 3, what do I get back? That still waits for the vector to be gone, okay? And inside, I will have this recursive call of n buried that will eventually look up like all these indices, right? The countdown on my I. So that would mean this code isn't really doing the work up front, right? All it's doing is, oh yeah, you gave me the first argument, great. And then it will sit there and wait, okay? It's going to be really lazy, essentially, right? It sits there and waits, and I'm not going to do anything besides, unless you give me the second vector. So we don't want to write it like that. Okay? We want to write it essentially that if I give you this, it will always generate this kind of function. And we would like to have a type system that will guarantee that, yes, okay, you are coding this in such a way that I can always run this partially and get meaningful closed code back. Okay? So what I want to do is I want to say, this is going to be a box. So this will force me to write this program in a very specific way. Namely, okay, we'll say if n is 0, if it's not good 0 as a 0 element, I will get the box as a function. It waits for this vector, and then I'm going to get the head of that vector. Okay? All right, so what do I do in the n successor of n case? Okay, S of n. Well, I need to compute the result of n minus 1. Okay, so I'm going to say let box. I'm going to get some result. So compute this by n of n, okay, which is essentially n minus 1. Okay. And then I'm going to make sure that I'm going to generate a function. So it's going to be waiting for the vector. Okay. And now what do I do inside here in the body? What I should be doing inside?
You need to use R in some way.
I need to use R in some way, and I can, okay, because, well, I used let, okay, that means R is now my valid piece of code, okay, that I can use inside my box. Okay, so I need to use R in some way.